Welcome back to the next Unit 2 video. As you can see, today we're going to be looking at some of the various network hardware. So a quick overview then. Well, the hardware we're going to look at, there's going to be terminators, repeaters, RJ45 connectors, bridge, hub, switch, both a wireless and just regular network interface card, also called network interface controller. We're going to see wireless access point, gateway, and router. We're also going to briefly look at routing tables, although we'll actually look at these more in detail, I think, in the next class. We're going to compare legacy versus modern Ethernet, and finally we're going to look at collisions and how they're actually handled, with something called CSMA CD, or carrier sense multiple access with collision detection. And that's a bit of a mouthful, so if you can remember that, that's quite good. Right, so I think previously then we've actually talked about some of these cables already. I think in last class. So we said so coaxial cables were the most common way to connect devices on a LAN, but that was, I don't know, maybe 30 years ago. These days twisted pair is going to be the most common, and we say fiber optic cables, these will be used to provide the backbone, so between cities, the undersea cables, for example for ISPs. So ISPs, if people don't know what, that's going to be internet service provider. So basically the company that, the company that kind of sells you the internet connection. And I mean, hopefully people can remember from last class, sort of the benefit of, coaxial, twisted pair, and fiber optic. So coaxial, we said, this was actually in the middle for everything, So it was the middle price, the middle bandwidth, the middle attenuation, interference. Whereas, so I guess if we look at twisted pair, this was going to be the cheapest, but then the worst for everything. And then fiber optic, this was the most expensive, but the best for everything. Now you might be thinking, why are we going to use twisted pair? And that's because, if we're just talking about home setting, then actually twisted pair, this can still support up to I think they said 40 gigabits per second. So honestly, so I guess just for a home connection, 40 gigabits per second. I mean that's more than enough. Of course, we don't need fiber optic, going into our laptop or into our desktop. It's just kind of overkill. Alright, so if we look at bus topology, and hopefully people can remember this, of course, what if we have one device, or let's say, this workstation here, if they're sending data, of course, they're sending it onto this central bus line, remember, this is going to be broadcast to everyone, and then, let's say it's intended for this one, but the thing is, it's also going to be sent to this device, it's also going to be sent to this device. So what they're going to have to do, they're going to have to check them, they're going to have to check the destination MAC address, to make sure that the destination MAC address, let's say to make sure that the destination MAC address, that this person sent, is the actual MAC address of this, of this device, because, so so I guess if we do a MAC address, I mean, it's going to be 12 hexadecimal characters, so I'm not going to do the whole thing, but basically, of course, that way again, it's going to send the destination MAC address. And then of course when it sends, if it gets to this computer and this device thinks, this MAC address that we're sending it to, is not my MAC address, then of course it's going to reject it. However, if this computer gets it, and of course, if this is its MAC address, then it's going to, accept these frames, accept this data. So, let's think then, why do we need terminators? Because, otherwise what's going to happen? Is that right? Okay, here we go. So as we send a signal along this bus line, it's going to get to the end, then it would bounce back. And of course, that's going to cause interference, So as it's bouncing back, it's going to interfere with the main signal. So that's why terminator, it's going to be a resistor that absorbs the electrical signal, just to stop it from bouncing back. Stop it reflecting. Alright, so hopefully that makes sense. Right, then if we look at repeater, so if a line is long, e.g. bus networks and long distance fiber optic cables, and I think this second one especially, then due to attenuation, repeaters are needed to retransmit the signal at full strength. Right, so remember that fiber optic has the lowest attenuation. However, since fiber optic is usually used for long distance, between countries, between continents. Of course, we're going to need repeaters, and I think they say that for fiber optic, repeaters are only needed every 100 kilometers. But of course, if you're sending data, 5,000 kilometers, over the Atlantic or over the Pacific, then of course, you're still going to need 50 repeaters. So basically, what we're saying with this is, if we draw the same graph again, so this is the distance, and I guess here, let's call it I, the intensity of the signal. So what we're saying, I guess the signal is going to be stepped like this, It's just going to decrease over time. and then right, yeah, I don't know. Okay, right, okay, so let's say here this is 100 km. So after 100 km, what then we're going to have a repeater, and this repeater is then going to just boost the signal again, or amplify the signal. Of course, back to the original. Then of course, well, I guess 200 km. Well, of course, well, then we're just going to boost it again. So hopefully that makes sense why we need that. Of course, just to stop signal loss due to attenuation. Right, so we can also have repeaters for wireless networking. So, for example, Wi-Fi phone towers. Right, and this may be because of distance, right, or because of obstacles such as walls or hills. And I think this diagram is actually quite good. It shows you quite clearly. Of course, well, obviously they can't send directly, right? Since there's a hill, there's a mountain in the way, right? Therefore, of course, well, it's got to go up to here. Then it's going to be retransmitted, back, this side of the hill. And of course, that's why they're going to build sort of radio towers, mobile phone towers, like at the top of the hill, on high altitude. Just so it has a good vantage point, right? It can send to everyone. Right, then the next thing, this is not really a hardware. I guess it is hardware, but basically it's just the connection. It's just the end part. Right, so twisted pair cables are going to contain RJ45 connectors at either end to allow data transfer. And I guess you can see, maybe it says here, no, probably not. So if, okay, so if we look here then, probably they're going to be just copper. Maybe you might even get some gold plated, if you want like really, fast. But yeah, right, okay, so like probably these are just, copper pins. And of course, well, these copper pins are going to connect, right, to the twisted pair cables. And of course, this is then used, just to connect it to your, laptop, desktop, your, I guess, router switch hub. And of course, right, the other end, we're connecting here, right, to the computer server. Alright then, if we look at a bridge, so a bridge is a device used to connect different LANs together and let them function as if they are a single network. Right then, I guess again, we're going to have an RJ45 connector right on a twisted pair cable, right, from a switch or hub, right, that's going to connect to the ports. So what we're kind of saying is, well, if we have, right, okay, let's say, well, this is our sort of LAN 1, right, okay, well, let's do another one here, right, this is, well, let's call it LAN 2. Now, a bridge, right, right, okay, so I think, for me, the way I like to think of it is, well, if you think of sort of, geography, right, obviously, a bridge is going to be used to connect different islands. So, this here is kind of what, like, island 1, right, this is island 2, right, then, of course, what we just have, the bridge between the two, right, just to connect them, just to join them together. And hopefully that makes sense, and, also, well, of course, what it's saying is what the twisted pair cable is just going to plug into the back of the bridge, right, in order to, sort of join all the networks together. Right, then if we look at hub, and to be honest, like, I've actually used the same picture here because honestly, like, from the outside, they're all just going to look the same. Right, so hubs are actually, well, almost never used these days, but they might still be mentioned. So when a device is on a LAN, right, sends data to a hub, then it's going to be broadcast to all other devices on the network. Now, this might be suitable in some cases like video streaming. Also if we have, I don't know, maybe we want some sort of data redundancy, where let's say, okay, we have one device, right, if it sends here to the hub, okay, let's say we want this data to be copied, right, as backup to, two different devices. So I guess if there's some, specialist application, right, maybe a hub can be used, but probably, in most day-to-day applications, probably we actually want to specify, well, right, okay, like, right, okay, so I guess we want to specify, right, if we're sending unicast, multicast, or broadcast. And hopefully people remember, well, unicast means sending only to one person. Well, multicast, that means, sending to, multiple different people, right, multiple different devices. And of course, broadcast, that's, just sending to everyone. Right, then if we look at a switch, and again, same picture because, from the outside it's going to look the same. Right, so it's going to store the MAC address and sometimes IP address, right, of the devices on the network. Right, a device will send frames, and we can also call that packets. Technically, like, right, if it's inside the network, okay, if it's just using the MAC address, right, then it's going to be called a frame. If it's actually going outside the network, okay, if it's also including the IP address, right, then you would call it a packet. Honestly, like, for the exam, I think if you call it a packet, it should be fine, right? They're really not going to care. Because to be honest, right, this is more of an A2, right, the difference between, frames, packets, right, the different layers of the OSI model. Right, and anyway, so right, okay, so a device is going to send frames, right, or packets, right, and these frames are going to contain a destination MAC address, right, this will be sent to the switch, which will then forward it out of the correct port to a device, right, based on its MAC address table. So basically what that's going to have, well, hang on. Yeah, right, okay, I mean, if I can even write. Right, okay, so right here is going to be the MAC address, and well, here is going to be the ports. So the port, I mean, we can probably just see, okay, here we go, yeah, port 1, port 2, port 3, port 4, right, etc. Or in fact, actually, I think it's going this way, right, 1, 2, 3. So let's say, well, port 1, port, 2, port 3. Now, let's say, for example, I don't know, okay, maybe device 1, right, this might have the MAC address, let's say A1, or let's say B2, or let's say C3, right, D4, what's going to be E5, and let's go F6. Right, since there has to be 12 hexadecimal digits. Right, of course, well, yeah, okay. Right, let's say device 2, of course, right, that's going to have a different MAC address, right? Device 3, that's going to have a different MAC address. So let's say, for example, okay, well, if this device is wanting to sending to, I don't know, all right, let's say this is, D4, or something. So, right, if this device is wanting to send to this device, well, of course, what's going to happen? Yeah, all right, okay, so, right, okay, so let's say this device is going to send to the switch, and I'll just say that's S here. Of course, what the switch is then going to look, and it's going to see, well, okay, this is the MAC address that they've added, to the frame. And then because of that, well, then it's going to send the data out of port 3, which of course here, right, well, that's going to be this port here. So yeah, hopefully that makes sense, right? The switch, well, it's just going to contain a MAC address table, right, which contains, well, the MAC addresses, right, then just, well, mapped to the port that, that device is actually connected to. And yeah, again, we said, right, supports, well, unicast, multicast, and broadcast. Because, well, I mean, if you think, of course, well, if it wants to send to every device, well, then, of course, it's just going to send out of every port. Of course, yeah, if it wants to send out of one port, or if it wants to send out multiple ports, yeah, of course, right, all of that is going to be supported. Then let's look at the network interface controller, right, also called network interface card, or yeah, shortened to NIC. Right, so there's going to be an Ethernet port connected to the network interface card, and well, that's just the green circuit board in the picture. So of course, what here is going to be the Ethernet port. Of course, yeah, well, I mean, obviously, yeah, this right green circuit board, that's the network interface card. Right, so the network interface card is going to do a lot of things. One's going to establish the initial connection. I guess, yeah, maybe doing various handshakes, just making sure the device is available. Right, then it's going to handle the main communication, and that's going to include things like buffering. So buffering, well, let's say we have, I don't know, yeah, A is sending to B. Now B here, and then right, okay, so yeah, okay, let's say that, well, we're the receiver, right? I mean, we're B. So, well, B is going to have a buffer attached to it. And yeah, I don't know, okay, maybe this is like the CPU or the memory or whatever. Now, what's going to happen? Well, of course, right, A is going to be sending data to B. Now, if, for example, I don't know, okay, yeah, maybe this is sending at like 100 megabits per second. But B can only process the data at 50 megabits per second. Well, in that case, of course, what's going to happen? Well, right, of course, yeah. So A is going to be sending data into the buffer. This buffer is actually going to start to sort of slowly fill up, since, of course, well, I mean, what we're sending faster than we can actually process it. And I suppose, well, right, of course, yeah, eventually, well, A is going to stop sending, and of course, well, when A stops sending, well, that's when the buffer is going to start to empty, because of course, well, yeah, obviously, like, B is going to continue processing that data, but yeah, A is not sending anymore. And I suppose, well, if the buffer fills up, well, yeah, then, of course, right, A is not going to be able to send anymore, right? It's going to have to wait. And actually, I mean, that should be controlled by TCP, yeah, just kind of like establishing, how much data can be sent. Yeah, based on whether B is available or not. Right, okay. There's also going to be things like error correction. This can include things like parity, which we'll look at later. I think in real life, it's going to be more sophisticated than parity. But yeah, I mean, parity is mentioned. I think in, I don't know, maybe chapter 8 or chapter 9, or yeah, I guess unit 8, unit 9. Right, and then also things like interrupts. So that can be, well, let's say if the buffer is full. Yeah, that can be if there's some sort of error. Yeah, I guess various other things. Right, the network interface card, well, this is actually going to store the, well, I guess, yeah, okay, it's going to store the device's unique MAC address. And this MAC address is actually, kind of, well, hard printed onto this. I think I guess in reality, like, I think it is actually possible, there's some sort of hacks around it. But technically, like, it should actually be impossible to change the MAC address. Although, yeah, I think, some people have managed to actually kind of, make their own hacks to actually change it. Alright, and then finally, I guess it's going to perform encryption, decryption, of course, yeah, just over the network. And, like, honestly, I mean, this is not an exhaustive list, there's going to be more things, but yeah, that's just some of them. Alright, so well then if we look at the wireless network interface controller, right, or again card, and if we notice this, well of course it's just the same, right, but just wireless. So right, it's going to provide the same features well the network interface card, right, but just for wireless communication. Right, e.g. well Wi-Fi, Bluetooth, I guess if it's a phone, right, also mobile networks. Right, so well okay, yeah, wireless network interface cards are going to contain an antenna. And yeah, I'm not sure which of these would be an antenna. I don't know, like yeah, I guess like maybe one of these might be the antenna. Where that's going to well transmit and receive wireless signals, and then again it's just going to do the same, right? So it's going to establish the initial connection, handle the communication, say well buffering, error correction, interrupts. It's going to store the device's unique MAC address, and again right encryption, decryption. So yeah, just the same as a network interface card, right? But also providing the wireless capability, right? The antenna to transmit and receive. Alright, so yeah, let's kind of take a break from sort of new devices. Yeah, let's focus on these then. So it says, right, can you think of devices that have both a wireless network interface card, right, and a network interface card? And I guess right in typical cases, of course, if you want both of them, well, it's just going to be one board that has both of those features. So yeah, I mean, have a pause, right? See if you can think of a device that's going to contain two. So probably like most desktops are actually going to support both, right? Because if we think desktops, they should support both a wireless, and wired connection. Yeah, I mean, like definitely they're going to support wireless now, and most of them, if you're thinking like a gaming PC, right? So yeah, I guess workstation. Then yeah, most of them are also going to have like an Ethernet port for a twisted pair cable. Thinking about this, right, we could have also probably said games consoles, so something like PS5, Xbox. Yeah, I think again they're going to support both wireless and wired. Right, some older laptops, again they're going to support both. However, these days, if we think of the sort of modern, thin laptop, then actually since they're too thin, right, most of them actually don't have an Ethernet port. Okay, yeah, most modern laptops are only actually going to support, yeah, okay, they're only going to support the wireless network interface card, yeah, or wireless connections. Alright, so yeah, I guess likewise then, can you think of a device that would only support wireless network interface card? And I think this one we just mentioned. Right, so if you pause that, yeah, again, have a think. Right, so yeah, I think this was actually going to be lots of our phones, tablets, home smart devices, right, the thin laptops, yeah, I guess also notebooks, right, anything that only supports wireless. Right, then alternatively, how about a device that might only have a network interface card? So something that's only going to support wired connections, right, not wireless. And this one's actually a bit, yeah, I guess a bit more difficult to think of. Right, I guess we can say, well, some servers are, probably like, yeah, these servers here we see in the sort of background picture. And yeah, I don't know, like, does it say? Yeah, okay, right, I think the next one we're going to ask why it uses that. Right, I guess also printers, right, something like CCTV cameras. Right, I mean, basically storage, right, so, well, network attached storage, right, or NAS devices. Right, these may only support wired connections. And I think here, well, now we're going to ask, so yeah, okay, right, thinking back to what we've learned, then why would servers use wired connections, right? So what's the advantage of using wired connections? So again, right, if you had to think about that, I guess, well, if we wire them in a star or mesh topology, right, well, then we're going to have a range of advantages. One, we're going to have higher bandwidth, of course, yes, faster than wireless communication. Right, it's also more reliable, it's going to drop less, yeah, I guess, kind of, less interference. Yeah, okay, right, so, well, no collisions, right, no interference. And of course, well, no collisions, right, if we're in a star or mesh topology. If we're in a bus topology, well, yeah, there will be interference. Although I think even these days, actually, a bus topology, right, can be wired in a way where there's no interference. Right, okay, I guess, like, if we're using full duplex wires, right, then a bus topology, yeah, is also not going to have collisions. Alright then, well, finally, just high security, because of course, what is yeah, it's going to be a guided connection, right? We're just going to have a point-to-point guided connection. It's not like wireless, where of course you have wireless, the signal's going out in all directions. Yeah, alright, so I think hopefully that makes sense. Right, and also longer range, because if you think Wi-Fi, I think they said Wi-Fi generally has a range of 20 to about 150 meters, or absolute maximum. Whereas of course, well, wires, generally we can just keep adding more and more wires. Of course, well, we will need a repeater, possibly. But yeah, generally the length of the wire is not really an issue. Alright, so yeah, let's go on to the next one then. Well, wireless access point, or again, yeah, well, just as you see the abbreviation. Right, so this is going to be the central device in the wireless LAN. Right, well, that's a wireless access point. Right, a home router is also going to provide this functionality built in. So what it's going to do, well, it's going to receive and transmit the wireless signal via the antenna. So of course, well, the antenna, right, just being this thing. Right, if a client has a wireless network interface controller, right, well, yeah, WNIC, then it should be able to connect to the wireless access point. Yeah, and I mean, well, hopefully that makes sense, right? Of course. Right, okay, so right, yeah. If we say, well, this one has an antenna to transmit and receive the signals, right? Well, yeah, okay, so right, the wireless network interface controller, of course, well, this is also attached to another antenna, again, just to transmit and receive the signals. And if we just go back, well, of course, well, that was going to be the one. Yeah, okay, for example, here, I don't know, like, yeah, maybe this one is the antenna, for example. All right, and then yeah, let's look at a gateway. So a gateway is going to act as the gate to a network, i.e., packets entering or exiting the network will pass through it. So right, we can also say it can convert incoming or outgoing data between different protocols. So yeah, if we have I don't know, okay, maybe from the network we have sort of protocol A, right, of course, but okay, let's say our network operates on protocol B. Well, of course, then the gateway, of course, what it can do, right, it can convert the packets on protocol A. And well, of course, right, I mean, here it's going to convert them, and obviously at this point right now they're going to be in protocol B, right, so they can be understood by the network. Right, and well, this can also act as a firewall to allow or block packets based on certain criteria. And if you think about that, well, that makes sense. I mean, well, since it's the gate to network, right, is well, I guess all the incoming and outgoing packets are going to have to pass through it, right? Therefore, well, based on certain criteria, right, either we can allow those packets through or block them. And some of the criteria, I mean, I think we've mentioned this. Well, I mean, certainly in the past paper videos. Yeah, maybe not this these syllabus videos. But well, the criteria. So there's actually a lot of things for this. One, it can be the IP address. So for example, okay, we can block either an individual IP address, right, or we can block an entire range of IP addresses. And sometimes you'll see this where, let's say, some websites you can't access from a certain country because, well, of course, all of the IP addresses in that country have been blocked, based on the IP address range. Right, I guess another thing we can block, well, it's going to be based on the port. So let's say we have, I don't know, I think port 21 might be FTP. Yeah, maybe 22 or 20 or something like that. Yeah, I think one of these is going to be SSH. So if, for example, we don't want people accessing these protocols, because again, right, I mean, FTP, file transfer protocol. So probably we don't want random people, sort of trying to upload and download files, from our server. Likewise, SSH. Well, we don't want people, logging into our server, right, getting access to a terminal or command prompt. So of course, what we can do, well, okay, so basically we can say, well, any packet that's using that port number, right, of course, we can just block that. You can also block based on things like heuristics. So if we have I don't know, one device or some collection of devices that are sending huge amounts of data, well then if they're sending way too much, well then that can be, I guess, kind of an indication of what either a denial of service, right, just from a single device, or if it's multiple devices, what then distribute denial of service, right, DDoS. Yeah, and I guess you can sort of also block on other things, right? I mean, you can use something called deep packet inspection, right, trying to actually look at the contents of the packets. But I guess I think IP, port number, and then sort of basic heuristics like how much data they're sending, right? That's going to be common things you would block on. Right, then I think finally, well, the final network hardware is going to be routers. Right, so technically routers only route, right, so direct or forward packets, right, data, right, to the next location, or to the next destination, right, the next hop. However, what people call a router in a home actually provides the functionality, well, not only a router, right, but I think as mentioned, right, also a switch, also a bridge, also, of course, right, a wireless access point, right, also a gateway. And I think we've said this, but of course, well, a router, right, is going to combine all of this functionality, right, into a single device. And right, again, so this is going to be, a home router. Now, if, for example, we're talking about, this router here, which is probably I don't know, okay, that's probably let's say the bottom of the ocean. Well, if that's at the bottom of the ocean, or, I don't know, some, underground cable, well, of course, I mean, that's not going to need to be a wireless access point, right? Since, there's no one at the bottom of the ocean that's, trying to use the Wi-Fi. So, right, okay, so I guess, okay, if we look at this, so, if, right, here we are. Okay, so if we see this diagram, well, probably, okay, this router, since it's the first one, of course, right, this is going to be their home router. So this one is probably going to provide, all the functionality of, I guess, all these other devices. Right, however, again, if we look at these kind of random routers here in the, in the middle of the network, well, I mean, they're not going to do any of this, right? Okay, they're only going to be used, right, just for routing, right, forwarding packets, right, to the next location. And I think like, well, here I didn't give you the answer because yeah, we're gonna look at this in a couple of slides of yeah, kind of why they actually combine all of this right into one. Right, so well, yeah, I think we said that. Yeah, so of course, right, where like an undersea cable router, right, it's not going to need all these extra functionality. And I think, I mean, here you can actually see, so this is going to be, well, just the fiber optic cables, and of course, yeah, the fiber optic cables are going to be contained right inside this. Right, so yeah, then if we look at routing tables, and we're just going to sort of look at this briefly, right, we're going to look in more detail, I think, next class. So suppose device, well, 12.001 wants to send to 14, right, 001. Then can you figure out what path the packet would take? Okay, like if for example, you know, you look at the routing tables here, right, in this network. So what we can see, well, right, okay, so yeah, okay, right, let's try to find network 12. So network 12, well, of course, that's this one. And let's say, for example, I don't know, okay, right, this, yeah, okay, right, this is, okay, yeah, that's been, okay, so this is, I don't know, yeah, 12.001. Yeah, I don't know, maybe this one is, well, 12.002. Of course, well, that's going to be 3, that's going to be 4, that's going to be 5. So what's going to happen then? Well, okay, first, okay, here we go. Right, first it's going to send to the switch. The switch is going to look and it's going to see what the destination is in this format. Okay, well, 1400. Well, then when we say 8, like again, we're going to look at this in a future video. But what that's saying is saying, well, 24 bits, right? Yeah, the first 24 bits are going to be used to represent the network, right? And then, well, the last 8 bits, so this 0 at the end, right? The last 8 bits are going to be used to represent the device on that network. So what that's saying is, well, so yeah, right, okay, so here, right, the network is, well, 14.0.0, okay, then the device is just going to be, well, device 1 on that network. So what it's saying then, okay, well, yeah, if, right, okay, if the destination IP is in this format, or yeah, I guess in that range, right, then we want to send it to, well, yeah, router 1. Yeah, okay, and I guess, hang on, right, okay, so, well, of course, you know, first it's going to, yeah, router 2, because that's, well, yeah, I mean, that's the gateway, right, that's the router for our network. Alright, then, well, from router 2, again, you know, based on this. Alright, then, of course, we're sending to router 1. Right, then, let's look at, well, router 1's routing table, where, of course, well, here it's saying 14. And, yeah, of course, right, that's saying, well, send to router 4. Alright, then, if we look at, well, 4, so, right, here we go. So, okay, 14. Well, now it's saying direct, so I guess, yeah, just internal, right, yeah, within the network. So, I guess here, well, let's send it to the switch, then. And then, of course, well, the switch, right, then the switch is going to know what device to send it to. So probably, I don't know, okay, right, okay, let's say this one is like, yeah, 14.001. Right, then, of course, well, it's going to send it to this device here. Yeah, so hopefully that makes sense. Like, again, what we can say, well, the root, okay, so yeah, so routers are going to have a routing table, you know, sort of stored in their memory. And what the routing table is, like, basically it's going to contain the network ranges. And then, yeah, based on that network range, well, then it's actually going to have, right, yeah, well, okay, yeah, right, okay, let's say, right, then it's going to store where to actually send it to next, right? It's going to store the next device, right, the next router, the next hop to actually send it to. And I think, yeah, if we just look at that, right, then we see, well, how about if, yeah, 12.1, right, sends to 12.2. Well, of course, well, in that case, well, since it's going to be direct, it's internal. Of course, well, I mean, well, then it's just going to go to the switch. I mean, I suppose, yeah, maybe it's going to go to the router, but, I mean, honestly, if you're using the MAC address, right, it can just, you know, stay in the network. And yeah, just, well, directly send it here. Yeah, I guess, you know, okay, without ever leaving the network. Yeah. Right, so yeah, this is the question then. So why do you think that a typical home router performs the function of, well, router, switch, bridge, wireless access point, gateway, right, etc.? So yeah, like, it's not really a technical reason. I mean, basically it's just convenient, right? It's going to make it easier for the home user. Well, yeah, of course, you know, regular people don't want 5 different devices, right? They're going to want one device that does everything. And to be honest, like, it's also cheaper for the manufacturers, right? If you, yeah, okay, if you think for the manufacturers, right, of course, it's cheaper to combine everything into a single device, right, rather than having to, you know, manufacture, you know, distribute 5 different devices. Right, I guess in contrast, someone like a business, well, they might have a more complex, or I guess, yeah, more specialist setup. Then, for example, they might have, let's say, many wireless access points, but only one router. Or yeah, I don't know, yeah, they could have sort of multiple switches, yeah, multiple bridges. I don't know, yeah, maybe one gateway. So if you want some more complex setup, right, then of course, well, yeah, I guess a business might do that, right? They might want a separate router, right, a separate switch. But again, you know, for a home user, right, just combine everything into one, right, makes it easier. And I will actually say, yeah, maybe I should have mentioned this. There's actually a program, like, if anyone wants to actually kind of have a go at making their own network. I think it's called, what, Cisco Packet Tracer. And of course, well, Cisco being the networking company. Now, if you actually do this, basically what it is, well, it's just a program where you can kind of drag and drop routers, right? Drag and drop switches, drag and drop, laptops, phones, satellites, right? All these different networking devices. You can then try and, configure the network, right? Using the IP, the MAC address. Subnet mask, DNS, right? DHCP, right? All of this stuff. Now, this is actually like, okay. I mean, right, okay. So obviously, I mean, that's not required for the exam. But if people are just interested, and of course, I mean, that is also good practice because, well, if you can actually do this, right, if you can, make the network yourself, well, then, of course, that's kind of proving that you actually understand how it works, right, at a deeper level. If you do want to see that, well, of course, I mean, just go on YouTube, right, type in, Cisco packet tracer, videos. Of course, there's going to be various tutorials about that as well. Right, so then if we just look at, well, Ethernet and Wi-Fi, and in particular, well, the IEEE, right, I think, right, the Institute of Electrical and Electronics Engineers. Right, so actually, well, in the book they mention this, although, well, actually, this has never been in the exam. Right, so Ethernet, well, they just call 802.3. Right, this is further categorized into 5 generations. So, well, standard Ethernet, right, fast gigabit, 10 gigabit, and 100 gigabit Ethernet. Right, Wi-Fi, so 802.11. And to be honest, like, maybe people have actually recognized this number. If they go into, I don't know, okay, well, let's say they go into their, Wi-Fi settings or their, phone settings or something. Right, often you'll see this. So, well, of course, right, you'll see the IP address, you'll see the MAC address, the subnet mask, right, the DNS server. And often it's also going to have, the Wi-Fi, the kind of specific Wi-Fi protocol. Okay, right, so actually here it doesn't say, but there's actually going to be different letters, like, I don't know, you might have sort of, 802.11a, maybe G, I think there's also C, there's N. I guess various different letters, right, which, well, as we see, right, that's, well, based on variations of the specification. And if we see the 802, well, that's actually quite simple, and that comes from the fact that the first meeting was held in, 1980, and I guess February. Just combining the year and the month. Right, so to look at an example then, well, if you actually look at, an Amazon advert for a router, then, well, of course, right, you can see the connectivity technology, right, okay, here we go. Right, of course, well, so, right, okay, so here it's saying it supports Wi-Fi, of course, well, that's what based on the antennas, right, the wireless access point. Right, it's also going to support Ethernet, so of course, Ethernet is going to have, the Ethernet ports at the back, right, of course, where you can plug in the twisted pair cables. Frequency, I guess, like, right, okay, so I think, well, when it says dual band, well, that's like the 2.4 gigahertz and 5 gigahertz, so that's basically saying it supports 5G. I think that's what that's saying. Right, then if we look at the wireless type, so again, here is where you can see all the different, like, sort of, kind of variations of the protocol. Security, right, that's just the various encryption it supports. Ports, okay, right, here we go. Of course, right, ports, that's going to be the number of Ethernet ports on the back. Then, of course, just the bandwidth, voltage. Right, so if we look at legacy or old internet, so as stated, hubs were used about 30 years ago, and they would broadcast all data to devices. And as mentioned, well, in some cases, right, let's say video streaming, right, maybe if you want to back up all your data by, broadcasting to multiple devices, right, in some cases that's okay. However, in regular day-to-day use, you probably want to be a little bit more, kind of selective in terms of, you only want to send to, this device or maybe a couple of devices, right, not every device. Right, okay, so, like, actually, probably, alright, let's change that. Okay, that should be the MAC address. So a receiving device would then have to check the MAC address, let's say in the packet. I mean, we can also probably say frame, to be honest, right, and determine if it was intended for them or not. And I think, this one we've said already. Right, so bus topologies work the same way. I think this is what we said. Right, so data is sent along the public bus line. Right, all clients will receive it, and we'll have to check if it's intended for them. Again, based on the MAC address. Now, sometimes they might use the IP address, but I think, in most cases, bus topology, right, it's just going to use the MAC address, since it's a LAN, right, they, don't really need an IP address. Right, so I think the final thing then, collisions. So if you're using a shared medium for transmission, right, e.g. bus lanes, right, for data transfer, then that means there can be collisions, and, that's two devices transmitting at the same time, which causes interference, and the data to become corrupted. And I think, this we mentioned in, previous videos as well. Now, and this is weird diagrams, right? It's kind of the wrong way up. So I guess, right, okay, this first one's actually the resultant wave. Now, let's say here, this is obviously wave A, right? This is wave B. Now, if we have A and B, right, if we combine them, well, since here, well, of course, we have a peak, right, and yeah, here we also have a peak, right, well, of course, then we're going to get constructive interference, and the resultant wave here, we're going to have, basically a peak that's, twice as high, or yeah, higher. Whereas I guess in contrast, if we look at the second example here, well, so okay, here we go, right. So of course, here we've got a peak, right, but then here we've got a trough. So this is going to be destructive interference, and of course, that's why it just cancels out. And then I think obviously we can see here, right. So of course, computer A, computer B, right, they're both transmitting at the same time, right. It's going to meet in the middle, right. That's where the collision is going to occur. Right, so this is where we're going to use an approach called CSMA CD, carrier sense multiple access with collision detection, right, and that's going to be used to solve this issue of collisions. Right, so let's see how it works then. Well, first we're going to check the voltage level on the wire, and if there's no voltage, well, this means there's no activity. No activity is good, right? Yeah, of course, right. So when we say no activity, right, that means no one else is sending, right? It's empty, it's free. Right, okay, so if there is a voltage, right, i.e. someone else is sending, right, then we want to wait a random amount of time before rechecking the voltage. However, right, if no activity is detected, and I guess we can also say, well, if we've waited a random amount of time, and the next time we check it, if there's no activity, right, the next time we check it, well, then we can start transmission, because of course, what this means, right, if there's no voltage, well, then no one is currently using the wire, right, therefore we can send. However, as we're sending this data, we want to continuously check for collision. Now, in theory, hopefully it shouldn't happen that often, because of course, okay, so once we start sending the data, well, the other devices shouldn't actually, let's say, right, the other devices shouldn't actually start sending data, if they've already registered that, we're transmitting data, because, of course, that's point 2, right? The only situation this is going to occur is, all right, let's say this is device 1. Now, okay, let's say here, right, so we've sent the data to, this point of the wire, and at the same time, this one has sent data, here. Now, of course, as they're traveling, right, eventually they're going to meet in the middle. But if for example, we have this, all right, let's say 1, right, if we look at example 1, well, if we say that, of course, this device has, sent data and it's already arrived at this one, well, this one is not going to, suddenly start sending data, because, again, right, it's just going to do 1, and it's, since it's going to check that there is voltage, right, then, of course, it's just going to wait, right, it's not going to send. That's why collisions, probably they're not that common, since, of course, the speed of electrical propagation is extremely fast. So kind of immediately, nearly immediately, right after they start sending, right, the other people are going to detect that, someone is sending, right, therefore they're not going to start sending themselves. I don't know, maybe that made sense, or maybe just, more confusing. Alright, so, right, okay, so I guess, right, as we're sending, if there's no collision, right, then we're just going to continue transmission. I guess that makes sense. Right, however, if there is a collision, and let's just clear all this. Right, okay, so if there is a collision, then we're going to stop transmission, and we're going to transmit a jamming signal. So a jamming signal, that's going to be, I guess, some special signal, or some special, sequence of bits that are going to notify other nodes of a collision. Right, then we're going to wait random time, or wait a random time and try again. And I think here is probably going to say, so if 2 devices send at the same time, then why do you think both wait a different, right, random amount of time before trying to retransmit? And here I've said different. Now, this is not always going to be different. In theory, they could both generate, 0.05, right? Okay, they could both generate the exact same random time. However, in reality, right, it's probably unlikely, again, considering it's random. So maybe you figured out that, of course, okay. So let's say if they both wait the same amount of random time, right, let's say 0.01 seconds, well, then there's going to be another collision, when they retransmit again. Because if we think, okay, this is device 1, this is device 2, now let's say, okay, they wait 0.1 seconds, right, this one then starts sending, but then, of course, after 0.1 seconds, this one is also going to start sending. And then, of course, eventually, right, of course, eventually here we're going to get another collision. Whereas if you think, if they both wait a random amount of time, then hopefully, the random times they've chosen are going to be different. And, because they're different, therefore, right, the chance of collision is going to be reduced. However, I guess, if they're unlucky and they generate the same random time, well then of course they're just going to have to generate, you know, a new random amount of time, and they're going to have to try again. So yeah, this is always going to work. However, if you have, you know, a large bus network with, like, say, I don't know, you know, hundreds of devices, then you can actually have a problem where you can basically get a build up where, okay, let's say you have two devices that are trying to transmit, okay, but it causes a collision, right? And then, you know, because they're having to wait, because they're trying to retransmit, well then, all right, maybe at the same time you then have another device that's also trying to transmit. So, you know, now in this case, right, you have, you know, three devices that are trying to transmit. Right, of course, well then it's going to get even slower, right? Okay, then maybe you have, you know, device 4 that's trying to transmit. So you can actually get a situation where basically you get a complete deadlock in the network, because of course, well, I mean, yeah, as they're having to wait, you know, wait to transmit, well then no other device can transmit. So yeah, you're just going to get this kind of backlog, right? Yeah, just like a traffic jam with cars. Alright, so if instead then we look at modern Ethernet, well, this is going to use switches instead of hubs again, well, unicast, multicast, broadcast. Right, switches, well, they're going to store, well, I mean, again, you know, probably the MAC address table. I might store IP addresses, but yeah, I think usually just MAC addresses. Right, and these are going to send, well, packets, right, or frames to the specific devices. And again, yeah, well, okay, I mean, so just to recap, right, frames is going to be the name, right, if it only contains the MAC address. Right, if it's, you know, I guess if it's meant for the sort of worldwide internet, right, well then we're going to call it a packet, right, since it also, you know, contains the IP address. However, I mean, well, for AS, I mean, I think for AS, right, just call everything a packet. You're not going to have to distinguish between, you know, frames, packets. Yeah, I think another one, maybe they call them segments, right? That's going to be a different, different level as well. Alright, anyway, so here then, well, switches, well, I think, yeah, unicast, multicast, broadcast, right, we said that. Right, it's also going to support full duplex communication. So if you actually think of this, well, if we've got a full duplex bus line, well, then we're actually not really going to get many collisions. Because, well, of course, you know what, you can have one device sending this way on this wire, or of course you can have another device sending this way, you know, on a different wire. And yeah, since we've got, well, of course, you know, one wire kind of, yeah, going this way, right, one wire going that way, yeah, you shouldn't really get collisions. Right, and then we say, well, switches also have a buffer, yeah, I think we mentioned this, right, which can temporarily store packets, right, when under high load. Yeah, of course, what if the kind of incoming packets are sort of, well, yeah, well, okay, well, let's see, if the packets incoming are coming in at a faster rate, you know, then they can be passed on or processed. Alright, and then, yeah, I think this we said, right, so if using full duplex links, I guess, well, no. I mean, yeah, I'm not sure if that's 100%. I mean, like, maybe there's still a small chance, but yeah, I guess, you know, fairly low. And well, again, as mentioned, that's because, well, full duplex provides data transfer in both directions. So if A is connected to B, right, then there'll be a dedicated wire supporting data transmission from A to B, right, and another dedicated wire supporting wire transmission from B to A. Alright then, I think, well, let's have a recap of everything then. So give a simple description of, well, hub, switch, router, bridge, gateway, right, repeater, wireless access point, and, well, yeah, wireless, and also, you know, just regular, right, network interface card, or, yeah, network interface controller. So, right, pause the video, yeah, try and have a go at this, alright then, just, yeah, resume once you've done that. Okay, so let's have a look then. So we say a hub, well, this is going to connect devices on a network and broadcast all packets. Yeah, hopefully people know that. And I mean, if we want to expand on that, we can say, well, it's probably going to have an Ethernet port. So of course, yeah, you would then, you know, plug in the Ethernet port. All right, anything that comes into the hub is then going to be broadcast out of all the Ethernet ports. Right, I guess, yeah, as a kind of improvement on that, well, a switch, again, it's going to connect devices on the network, but this time supports, well, unicast, multicast, and broadcast. And this one is going to use a MAC address table, and it's going to send data out of the correct port, okay, based on that MAC address table. And of course, what the MAC address table, as we've seen, yeah, okay, so I guess, right, in one column it's going to contain the MAC address, right, and then what in the, you know, in the other column, in the other column, right, it's going to contain the port number, yeah, that, you know, the device with that MAC address is connected to, right, just so it can send the data out of the correct port, basically. Right, then it's going to be a router, so, well, that's going to route packets between, well, yeah, I guess, well, between devices or between networks, right, by sending packets to the next hop, right, based on the IP address table. And actually, like, yeah, alright, hang on, okay, alright, yeah, so let's call that a routing table, right, not an IP address table. Yeah, that's definitely wrong. Right, okay, so bridge, well, that's going to connect two network segments into a single network, so basically if we've got two LANs, right, we want to connect them into a single LAN. Yeah, that's really what that's saying. Right, then gateway, that's going to be an entry and exit point of a network, so it's going to connect networks of different protocols, and it can also act as a firewall, so what to, yeah, block or accept incoming and outgoing traffic. Right, then there's a repeater, so that's going to retransmit signals at full strength to prevent signal loss due to attenuation. And yeah, hopefully people remember that. Of course, what just the just that chart, right? So of course, what the okay, right? So the intensity is going to decrease, but then I don't know. Okay, let's say every 100 kilometers if it's fiber optic. Of course, well then we're just going to rebroadcast at the rebroadcast at the full intensity, right? The full amplitude. Right then, I think continued, right? So wireless access point, that's going to allow devices to connect wirelessly, and it has antenna to receive and transmit signals. And of course, well, I mean, again, like if this is a home router, well, a home router, of course, that's going to have a wireless access point built in. Right then, the network interface card, it's going to contain Ethernet port. This does a lot. Right, it's going to establish the initial connection. Right, it's going to handle communication. Right, for example, buffering, error correction, interrupts. So interrupts, well, for example, if the buffer is full, I guess if there's a hardware error, probably, I don't know, other things, right, maybe, based on the initial sort of handshake. Right, well, it's also going to store the MAC address, of course, what the MAC address hard-coded by the manufacturer, well, I guess kind of burnt onto the actual network card, physically burnt onto it. Right, it's also going to perform encryption, decryption. Then finally, well, the wireless network interface card, I mean, well, as above, right, but however, it's going to have no Ethernet port, but it's going to support wireless connections instead, I guess, via an antenna, right, to transmit and receive. And that can be, Bluetooth, so I guess, Bluetooth, Wi-Fi. And if it's like a phone, tablet, right, then, of course, I mean, that's also going to have, so, right, that's going to have something, just to connect to the mobile networks as well. Alright, then, I think maybe this is the last question. So, how are collisions handled on a bus network? And is this an issue on modern bus networks? So hopefully you remember what's called CSMA CD, right? Carrier sense multiple access with collision detection. Right, let's see how this works then. So we're going to check the voltage level on the wire, right? We said, if there's no voltage, no activity, right? No one is sending. Right, if there is a voltage, or i.e. a message, then we're going to wait a random amount of time before rechecking. And of course, well, I mean, so I guess, right, the reason we're waiting a random amount of time it's just so they don't both wait the same random amount of time. Because if you have two devices that are waiting, if they both wait the same amount of time, well, then they're going to try to transmit at the same time, right? Then we're going to get a collision. Right, however, if no activity is detected, right, then we can start transmission. Right, as we're transmitting, we're going to continuously check for collisions. Right, okay, if there's no collision, well, just continue transmission. However, if there is a collision, well, then we're going to stop the transmission and we're going to transmit a jamming signal to notify other nodes of collision. Right, then we're going to wait a random amount of time and try again. Alright, so guys, I think, right, that's everything in this video. Hopefully this video has been useful. Right, as always, any questions, just ask in the comments. And yeah, again, right, if the video has been useful, well, then see you again in the next video.